You already know how to turn a curve into its steepness recipe. Now flip the question. If I only hand you the recipe with the original curve erased, can you build the curve back? Keep that question parked. We're coming right back to it. Watch this curve slide straight up and down. Its shape never changes, so its steepness at any point never changes either. That means 2x isn't the recipe for O-N-E curve. It's the recipe for a whole family of curves, one for every possible vertical shift. So reversing a steepness recipe never hands back one exact curve. It hands back the whole family, written with a +c. We don't know which vertical shift it started at. This reverse process has its own name: integration. Start from 3 already known facts. Differentiating x cubed gives 3x squared. Differentiating x to the 4th gives 4x cubed. Differentiating x to the 5th gives 5x to the 4th. Instead of memorizing a brand new rule, just read each O-L-D fact backward. Divide both sides by the coefficient so a bare power is left, then read it the other way. Each time, the power goes up by 1, and you divide by that brand new power. That pattern held every single time, so let's write it once for good. Add 1 to the power, divide by that new power, and always tack on +c. That's the whole rule, and it earns its keep because we just watched it work 3 separate times. One power it can never touch is -1, because then you'd be dividing by 0. Now the recipe from the very start of the lesson gets a real formula, and we run our new rule on it. Then, to be totally sure, we differentiate our own answer straight back. It lands exactly on the recipe we began with. That round-trip check is how you confirm any integration answer. A plane number can look like it has no power to reverse at all. But every plane number is secretly x to the 0 power, hiding in plain sight. Reverse it exactly the same way as anything else, and a flat recipe still gives you back a real x term. A curve's gradient function is given as di over dx equals 6x squared minus 4x plus 5. Find the most general expression for y in terms of x, and verify the answer by differentiating it back. Integrate each term separately, using the power rule we just earned. 6x squared. Raise the power to 3, divide by the new power 3, giving 2x cubed. Minus 4x. Raise the power to 2, divide by the new power 2, giving minus 2x squared. And the plane 5 is really 5x to the 0 power. Raise the power to 1, divide by 1, giving 5x. Combine the 3 integrated terms, adding exactly one constant of integration, c, for the whole expression, not one per term. Check it. Differentiating 2x cubed gives 6x squared. Differentiating minus 2x squared gives minus 4x. Differentiating 5x gives 5, and the constant c differentiates to 0. Summed together, 6x squared minus 4x plus 5 exactly the gradient function we started from. The integration checks out. Y equals 2x cubed minus 2x squared plus 5x plus c, where c is an arbitrary constant of integration. Verified because differentiating this back gives 6x squared minus 4x plus 5, matching the original gradient function exactly. A different gradient function is given as di over dx equals 4x to the power negative 3 plus 2 for x not equal to 0. Find the most general expression for y in terms of x and verify by differentiating back. Integrate term by term again, this time tracking the negative power carefully. 4x to the power negative 3. Raise the power to negative 2 first, then divide by that new power, negative 2, giving minus 2x to the power negative 2. And the plane 2 is really 2x to the 0 power. Raise the power to 1, divide by 1, giving 2x. Combine the two integrated terms, adding one constant of integration, c. Check it, differentiating minus 2x to the power negative 2 gives back 4x to the power negative 3. Differentiating 2x gives 2, and the constant c differentiates to 0. Summed together, 4x to the power negative 3 plus 2, exactly the gradient function we started from. The integration checks out. Y equals minus 2 over x squared plus 2x plus c, where c is arbitrary, equivalently written as minus 2x to the power negative 2 plus 2x plus c. Verified because differentiating this back gives 4x to the power negative 3 plus 2, matching the original gradient function exactly. So yes, handed only a steepness recipe, you see, and rebuild the original curve, up to that one unavoidable plus c. Whenever you're given a gradient function and asked to find y, integrate term by term, raising each power by 1 and dividing by that new power, remembering a bare number is really x to the 0 power. Add exactly e constant, c, for the whole expression, because a whole family of vertically shifted curves shares that same gradient function. You can't tell which one it started as. Always check by differentiating your answer back. Any mismatch means an arithmetic slip. This same idea, applied to trickier expressions and pinned down with a given point, is what the rest of this chapter builds on.